In this video, let's take a look at some of those properties of standard deviation that make it such a useful statistic. And so we'll begin with what's known as the empirical rule. The empirical rule is this 68, 95, 99.7 rule. And it says that if our data follow a bell curve distribution, then 68% of the data will be within one standard deviation of the mean. 95% of data in our bell curve distribution will be within two standard deviations of the mean. And nearly all of the data will be within 3 standard deviations of the mean. So this picture right here nicely captures everything that I just said. You can see that we have a bell curve distribution and the mean is right here in the middle. If I deviate 1 standard deviation on either side of the mean, the empirical rule says that approximately 68% of my data is in that range. If I start at the mean and I deviate 2 standard deviations on either side of the mean, then 95% of my data is in that range. And if I start at the mean and I deviate 3 standard deviations on either side, you can see that I'm going to be covering almost all of the data. So let me give you a little bit of context here to make some sense of this. So let's think about an example where we are talking about the heights of adult men in the US. Now we know a little bit about the heights of adult men in the US. We know that their heights do follow this bell curve distribution. So the empirical rule will apply in this context. We also know that the population mean height of adult men in the US is 69 inches. 69 inches is 5 feet 9. And we know the population standard deviation is in the vicinity of 3 inches. So if I attach these numbers to this picture, we can interpret what the empirical rule tells us. And so if the mean is 69, and 1 standard deviation is 3 inches, then if I deviate 3 inches on either side of 69, I get a range from 66 to 72. And the empirical rule is telling us that approximately 68% of adult men in the US are between 5.5 feet tall and 6 feet tall. Okay, let's start at the mean and deviate 2 standard deviations on each side. So if 1 standard deviation is 3 inches, then 2 standard deviations would be 6 inches. So I'm going to deviate 3 inches twice to get down to 63 inches right here. And if I start at 69 and go up 3 inches twice, then that takes me to 75 inches. So again, the empirical rule says 95% of adult men in the US are between 63 and 75 inches tall. This is 5'3" and 6'3". And then if we start at 69 inches and we deviate 3 standard deviations on each side, this takes me down to 60 and it takes me up to 78. And so once again, the empirical rule is saying that almost all adult men in the US are between, in this case, 5 feet tall and in this case, 6 feet 6. And a lot of those statements that I just interpreted based upon the empirical rule make a lot of sense based upon, a lot of the people that you know. Okay, let's take a look at another example applying this empirical rule. So in this one, it says a data set has a mean of 20 and a standard deviation of 3. A histogram is shown here. Is it appropriate to use the empirical rule to approximate the proportion of the data between 14 and 26? If so, find the approximation. If not, explain why not. Okay, so when I first look at this histogram, do you see that we do have a histogram that has that approximate bell shape? It's not perfect, but for our purposes here, I think it's bell-shaped enough for us to say it is appropriate to use the empirical rule. So when I apply the empirical rule, I apply it a lot like I just did in the heights example. I'm going to note here that our mean is 20 and our standard deviation is 3. And so a lot of times I'll either draw a picture or I'll use a picture exactly like we have right here, and I'll just label the mean, and then I'll start deviating 1 standard deviation on either side. And if 1 standard deviation is 3, then deviating 1 standard deviation on either side gives me an interval of 17 to 23. Now the empirical rule says that 68% of my data is going to be within 1 standard deviation of the mean. So the empirical rule is saying 68% is between 17 and 23. Okay, so let's go back to our picture. Let's deviate another standard deviation. So that's going to give me a range of 14 to 26. And so in this case, we can clearly see the empirical rule is saying 95% of the data is between 14 and 26. And we could do this one more time. And if we started at 20 and we deviated 3 standard deviations on either side, then I get an interval from 11 to 29. And the empirical rule here is saying 99.7% of the data in our distribution is between 11 and 29. And so you can see that I've actually obtained all 3 pieces of information that the empirical rule gives me. And sometimes that's a really good strategy when solving homework problems on this stuff. But to answer our question, it said approximate the proportion of data between 14 and 26. Well, now we can clearly see that it's 95%. Okay, let's go talk about another rule right now known as Chebyshev's inequality. And this has some similarities and differences to the empirical rule. First off, Chebyshev's inequality is going to hold for absolutely any data set. And this is important because not all data sets have a bell curve distribution where something like the empirical rule can apply. So the Chebyshev's inequality says at least 1 minus 1 over k squared of the data in any data set is within k standard deviations of the mean. And that is pretty tricky and abstract when you read that. And so what I've done here, as you can see, is I've plugged in 2 different values of k, the 2 most common values of k that really make sense and apply with Chebyshev's inequality, k equals 2 and k equals 3. And so when I plugged k equals 2 in, notice the beginning of this becomes at least 1 minus 1 over 2 squared of the data in any data set is within 2 standard deviations of the mean. Well, 1 over 2 squared is 1/4. 1 minus 1/4 is 3/4, and 3/4 is 75%. So we're able to say at least 75% of the data in any data set is within 2 standard deviations of the mean. And when I plug k equals 3 in, I got 1 minus 1 over 3 squared, and that's 1 minus 1/9, which is 8/9, and 8/9 is 88.9%. So we also have the statement that at least 88.9% of the data in any data set is within 3 standard deviations of the mean. So these statements might remind you of what we talked about with the empirical rule, but remember with the empirical rule our percentages were a little bit different. In the empirical rule we said that 95% of the data in a bell curve data set or in a bell curve distribution would be within 2 standard deviations of the mean. And we also said that 99.7% of data in that bell curve distribution would be within 3 standard deviations of the mean. So these numbers are a little bit lower than what we saw with the empirical rule. And the reason is this is a more general type of a statement. These are more general statements. You see that they apply to absolutely any data sets instead of the specific bell curve-like distribution. Okay, so let's see how we can solve an example involving Chebyshev's inequality. So in this one it says what's the temperature? The temperature in a certain location was recorded each day for 2 months. The mean temperature is 62.4, and we have a standard deviation of 3.1 degrees. What can you determine about these data by using Chebyshev's inequality with k equals 2? So essentially we are going to be able to determine that at least 75% of the temperatures in the data set are within 2 standard deviations of the mean. So how do we denote 75% of the temperatures are within 2 standard deviations of the mean? Well, what you do is you create an interval and you say that interval is going to be the mean minus 2 standard deviations up to the mean plus 2 standard deviations. So all we need to do now is substitute in our mean and our standard deviation. And so this becomes 62.4 minus 2 times 3.1 up to 62.4 plus 2 times 3.1. If we can go over here to the calculator and compute this real quickly, 62.4 minus 2 times 3.1, whoops, I should just say is equal to, we get 56.2. And then the upper end of that interval, 62.4 plus 2 times 3.1, gives us 68.6. So if the question said, what can you determine about these data by using Chebyshev's inequality with k equals 3, then what you would have done is you would have begun this by deviating 3 standard deviations on both sides. But if you want to apply Chebyshev's with k equals 2, then we start with the mean, we subtract 2 standard deviations, and we go up to the mean plus 2 standard deviations. And so our final interpretation of this question based upon Chebyshev's inequality is that at least 75% of the temperatures in this particular data set are between 56.2 degrees and 68.6 degrees. I'll say that one more time. At least 75% of the data being within 2 standard deviations of the mean in this context means at least 75% of the data in our temperature data set is between 56.2 degrees and 68.6 degrees. Okay, let's look at one more topic involving standard deviation, and this one is known as the coefficient of variation. We use the coefficient of variation a lot of times when we're comparing different data sets that have completely different units. So those data sets might have their own standard deviations, but comparing a standard deviation that has one type of units with a standard deviation that has a completely different type of unit doesn't make any sense. And so instead what we do is we look at the variation in each data set relative to its mean, and then we can compare the coefficients of variation. So the coefficient of variation is actually a really simple formula. We'll just be taking the standard deviation and dividing by the mean. The closer to 0 the coefficient of variation is, the smaller the standard deviation is relative to the mean, and the larger the coefficient of variation, the larger the standard deviation is relative to the mean. So let's look at this example. It says National Weather Service records show that over a 30-year period, the annual precipitation in Atlanta, Georgia had a mean of 49.8 inches with a standard deviation of 7.6. Okay, and then the annual temperature had a mean of 62.2 degrees with a standard deviation of 1.3 degrees. Okay, so precipitation and temperature, that's kind of what we are comparing here. Compute the coefficient of variation for precipitation and for temperature. Which has greater spread relative to its mean? And so we've got precipitation and temps. Now the coefficient of variation for the precipitation is going to be the standard deviation of precipitation, so that was the 7.6 divided by the mean of 49.8. And we can punch this into the calculator and see what we get. 7.6 divided by 49.8. 49.8, and that gives me 0.1526. And then the standard deviation, or I'm sorry, the coefficient of variation for the temperatures would be 1.3, because that is its standard deviation, divided by its mean of 62.2. And so if I do 1.3 divided by 62.2, I get an answer of 0.0209. And so you can clearly see that this coefficient of variation for precipitation is greater than the coefficient of variation for the temperature data. And so this suggests that there is more variation relative to the mean for the precipitation data than there is for the temperature data. And this is how you would compare the spreads in two data sets, again, that have completely different units. You want to use this statistic right here, this 0.1526 and 0.0209, instead of comparing the standard deviations themselves, instead of just saying, oh, well, 7.6 compares to 1.3. Okay, so I hope you saw in this video a few important applications of standard deviation. And again, standard deviation was a lot of times capturing the variation or the spread in our data. Now in the next video, we move away from statistics that capture the spread and variation in the data, and we're going to look at measures of position now. So check that one out next. Thanks.